Have you ever looked at a massive skyscraper or a bridge stretching over a river, or even just a phone in your hand and thought, what's stopping this from just breaking? Well, that's exactly what we're diving into today. The incredible, hidden science that keeps our world from literally falling apart. Structural reliability. And that, right there, is the huge question. It's the fundamental challenge for every engineer. We live in a world where everything, and I mean everything, from the biggest bridge to the tiniest screw, is constantly under stress, and, it's gonna fail eventually. So how do you build anything with confidence when you know that failure is a certainty? So where do they even begin? Well, it starts by facing a simple, universal truth. Failure is inevitable. The job isn't just to build something strong. The real job is to build something that can fight back against a completely unpredictable world for as long as humanly possible. And the real trick is, it's almost never just one thing that causes a break. It's this wild mix of countless random factors. A sudden spike in temperature, an unexpected amount of weight, or just microscopic wear and tear that adds up over years and years. All these things are constantly changing, which makes predicting that exact breaking point, well, it's like trying to hit a moving target. So how in the world do you hit a moving target? You learn to predict where it's going. And this is where we get into something that feels a lot like scientific fortune-telling, the entire field of structural reliability analysis. At its heart, it's all about using some seriously powerful mathematical tools to see into the future. It lets engineers look at a bridge or a building or a tiny little part in a machine and actually calculate the odds of it failing over the course of its life. It's pretty amazing. Now, engineers have this toolkit, right? And there are two main gadgets inside. First up, statistical models. Think of these like a weather forecast, but for failure. They look at tons of historical data on similar parts, use fancy probability math like the Weibull distribution, and from that, they can forecast future failure patterns. Then you've got computer simulations, like the Monte Carlo method. This is like having a virtual crash test dummy on steroids. You can run a test on a computer a million times, tweaking the conditions just a tiny bit each time to see all the possible ways something might break. Okay, so you have this amazing forecast, this super smart simulation. But at the end of the day, it's still just a guess, right? A really, really educated guess, but a guess nonetheless. And a prediction is totally worthless if you can't trust it. So, how do these mathematical guesses actually earn our trust? And that brings us to what is, without a doubt, the most important part of this whole process: validation. Every single prediction, every clever model, has to be put to the test against the cold, hard facts of the real world. And believe me, engineers have a whole arsenal of ways to do this. They're constantly comparing their computer models to what happens in actual physical lab tests. They analyze data from structures that are out there in the field. They use cool tech like sonic tomography, which is basically an ultrasound for a concrete pillar, and they run static load tests. And of course, they check everything against the established national and international safety rules. And this quote, man, it just nails the entire philosophy of modern engineering. It doesn't matter how brilliant your theory is or how powerful your computer model seems, the crucial step, the one that makes all the difference, is checking it against a real experiment. Your theory has to prove itself in the real world, period. Okay, so you've put your prediction up against reality. Now what? Well, now you got to keep score. Accuracy isn't just a feeling, right? It's a number. Engineers need a scorecard to know if their crystal ball is actually any good. And that scorecard comes in the form of what are called prediction accuracy metrics. They're basically just statistical tools that are designed to measure one simple thing: how big was the gap between what the model said would happen and what actually happened in the real-world test? A classic one you'll hear about is the root mean square error, or RMSE. The easiest way to think about it? It's like a golf score. The lower the number, the better you did. So a low RMSE score means your prediction was super close to the real result. That's great. A high RMSE, that means your model was way off, and it's time to go back to the drawing board. But that's not the only way they score things. There's another big one called R-squared, and with this one, it's the opposite. You want a high score. A high R-squared value shows that your model's predictions and the real-world results are moving together, that there's a strong relationship. It's all about proving the model isn't just getting lucky, but that it's genuinely reliable. So you might be thinking, okay, this is all fascinating math, but what does it actually do? Well, this is where it all comes together. This is not just some abstract exercise. All this complex modeling and testing and scoring has a direct, profound impact on the safety of the world around us. This is where the theory actually saves lives. For instance, think about all those incredible glass buildings you see downtown. This science is baked right into the building codes, like something called Eurocode 10, that spell out exactly how glass structures need to perform. It lets architects design those beautiful glass walls while making sure they stay safe, even if a pane of glass happens to break. Or what about the massive, complex machines that power, well, everything? Reliability analysis is what lets us predict when a tiny little bearing inside a giant engine is going to give out, and that prevents catastrophic failures that could shut down an entire factory or, worse, put people in danger. And it's not just for new stuff. It's crucial for the infrastructure we already rely on every single day. Engineers use these very methods to figure out if a building is still safe after something like an earthquake, or to predict and stop problems like wood decay in older structures before they become a real hazard. So here's the big idea to take away from all this. Structural reliability, it's not just about playing defense, just stopping disasters from happening. It's an offensive tool. It's what enables innovation. Because by understanding and predicting failure, we gain the confidence to push the boundaries of what's even possible to build. Which really leaves us with an amazing question to think about, doesn't it? As these predictive models get better and better, letting us build taller and lighter and more complex things than we ever dreamed of, what's the next impossible thing that this science is going to let us build with total confidence?